Okay, at this point in the class, we've brought atoms together, either neutral atoms or charged ions, to form different types of compounds. And soon we're going to talk about the chemistry behind the formation of these compounds and the reactions that these compounds can undergo to form even newer compounds. But first, before we do that, we need to be able to count atoms and molecules so that we can compare that to what we weigh out in the lab. Right? So we always want to connect the macroscopic world that we can see in the lab. We need to connect that to the microscopic world, which is atoms and molecules. So that means in lab, we're always working with masses of things. We're measuring them out on a balance. So we need to connect mass, which is in grams. That's what we're weighing out on the macroscopic level. We need to connect that with the number of atoms and the number of molecules that we're actually putting on the scale. Because when we talk about chemical reactions, we need to look at the actual atoms and molecules themselves. Now that's going to be a big number. Molecules and atoms are really, really tiny. So if we want to talk, we've actually put onto a balance, we're going to need some sort of counting in groups. So let's take a look at how that might be. Let's get a feel for what the masses might look like. So we've already said that if we have one carbon atom, we know that that atom has a mass of 12.01 atomic mass units. We did that in another lecture video, and we use atomic mass units because atoms are so small that measuring them out and measuring the mass of an atom in grams or pounds is just unreasonable. But let's see how many grams this corresponds to. We know there's a conversion factor that relates the fact that one atomic mass unit is equivalent to 1.66 times 10 to the minus 24 grams. Then I know that my atomic mass units are going to cancel out, which tells us that there's 1.99 times 10 to the minus 23 grams for one carbon atom, right? So that makes sense. That negative 23 exponent tells us that one atom has a really, really tiny mass. So we can't count out atoms and make relationships on a scale between single atoms and grams because we don't have a scale that goes that tiny in terms of numbers. So let's try again. Instead, we counted atoms by the dozen, the same way we do eggs. So if I had 1 dozen carbon atoms, then I know that there are 12 carbon atoms in that 1 dozen, because that's how many a dozen is. That's the definition. So 1 dozen carbon atoms. So that will tell me how many total atoms I have if I have a dozen. Then I'm going to keep going here with my multiplication. And I know that, again, 1 carbon atom has a mass of 12.01 atomic mass units. And then I'm just continuing my multiplication here, so my carbon atoms cancels out. And I know, just like in the last problem, there's 1.66 times 10 to the minus 24 grams in 1 atomic mass unit. So then my atomic mass units cancel out, leaving me with units of grams. So that tells me that if I start with a dozen, so I'm counting in groups of 12 now, then I come up with the fact that 1 dozen carbon atoms has a mass of 2.39 times 10 to the minus 22 grams. So that's all well and good, but this is still a really tiny number. So it doesn't make sense that I can count my carbon atoms in groups of 12 or a dozen either, because I still don't have a balance or scale that will measure out that small of an amount. times a charm. I'm just going to pick a different number now. So let's say instead of counting in groups of 12, I count in groups of 6.022 times 10 to the 23rd. That's a really big group. So let's say I have that many carbon atoms. Then we'll do the same calculation again. So we know that one carbon atom has a mass of 12.01 atomic mass units. So now we can cancel out our units of carbon atoms. That tells us how many AMUs we have, the mass when we have 6.022 times 10 to the 23rd carbon atoms. It tells us that mass in atomic mass units. And we know, if I keep doing my calculation, that there's 1.66 times 10 to the minus 24 grams in one atomic mass unit. So now our atomic mass units cancel out. And if I do that math, I get 12.01 grams. So that is a reasonable number, right? I could put 12 grams on a scale in the lab. And now what that's telling me is if I weigh out 12.01 grams on the balance, then that's, if I were to go down onto the microscopic level and count, I would have 6.022 times 10 to the 23rd carbon atoms. So now I have a relationship between the mass on the scale and how many atoms I've weighed out. And even better is look at the number. The number that I've put on the mass, for the mass on the scale, is the same as the relationship numerically between the mass of one carbon atom measured in AMUs. So let's take a look at these. So now what we're saying is that if we have one carbon atom, that's the equivalent of 12.01 atomic mass units. And if I have instead 6.022 times 10 to the 23rd carbon atoms, that's the same as having 12.01 grams. So what we're seeing here in this first equivalency is the relationship between the mass of one atom and its mass, and the relationship in the second equivalency between the mass of 6.022 times 10 to the 23rd atoms and its mass, that group of atoms measured in grams. Now it turns out in the same way that if you have 12 carbon atoms, we call that a dozen. When we have 6.022 times 10 to the 23rd carbon atoms, we call that 1 mole. Okay? So this number here, 6.022 times 10 to the 23rd, is also a special number. That's Avogadro's number. That guy's so famous, he's got a number named after him. So what this tells us, we can write some different conversion factors. We have 12.01 atomic mass units for every one carbon atom. That allows us to relate one atom to its mass measured in atomic mass units. Or we can say we have 12.01 grams for every 1 mole's worth of carbon atoms. That allows us to relate the mass in grams of an entire mole's worth of atoms, remembering the fact that 1 mole of atoms is the same thing as saying that we have 6.022 times 10 to the 23rd atoms. It's one really big group.